here's a little help on how to just tackle basic area problems in Polar. I'm going to make full screen here just a second so I can get my screen up and running. All right, the biggest deal is when you do polar curves, the ones we've looked at are like rose curves with the petals like a flower. We've done cardioids. We've done, I think there was one other that was kind of a limicons and dimpled limicons and things like that. Those are the big kind. There's one more lemniscate that we'll see here at the end, which is like a figure 8, and that's also one more that we want to know. But that's actually a pretty slick one. Oops, sorry, kind of coloring all over my screen when I try and scratch something off. But the way area is conducted in polar is you actually do sectors. So sectors are like slices of a pizza. You break up any area up into sector pieces. And that means basically the area formula for a sector is what we use. That's what you're seeing down here in this integral. It's just integrating the area formula for sector, just infinitely small ones like all the other integrals we've ever done. So if you take a circle and you think of a chunk of it being described by an angle theta, the area of the whole circle is, of course, pi r squared. So if I put an r in there, so it's pi r squared. But if you want to do, you understand that theta is a portion, a ratio portion of it. So theta is a portion of the whole thing, 2 pi. And it turns out that if you think of 2 pi as the whole kind of distance around angular wise, and theta being the part, you can use that ratio as a comparison for your areas as well. So the whole area of the circle is pi r squared, and then the area of the sector is the piece. And if we do this as like a proportion and you solve it on here, so theta over 2 pi is the same as area of the sector over pi r squared, that ratio is the same between those two, then you can solve that little proportion by doing some crisscross stuff right there, cross multiplication. And we end up with, and we're trying to solve for the area of a sector. So I take that back. We just want to multiply both sides by that denominator. We don't need to go all out, save ourselves some time, but we end up with area of a sector is, we call it sector area, around there, is pi over squared, that new denominator times theta over 2 pi. And if you notice, there's some nice cancellation that takes place. That pi cancels in each case, and all that's left then is this r squared theta over 2. So when we integrate, you see that here. Here's r squared theta over 2. Instead of over 2, it's a half. Here's r squared. And because we're doing an infinite number of those sectors that are infinitely thin, that theta gets infinitely thin. So instead of theta, we call it d theta, which is that approaching zero limit form of that angle. So there it is. That's what we integrate. That's how we do area. The only thing that's also slightly different is that the way we calculate the area is like a sweeping motion. So you start with the lower angle, and then you just do sectors sweeping circularly toward the upper bound angle. And it's always kind of a sweeping from the origin that takes place to calculate area. Now, let's take a graph that we know and love. So we got 2 plus 2 sine of theta is one of our graphs from the other day. It faces up and down. As any sine curve would, it's positive, so it faces up, positive as in this sign is a plus sign between them. When they have equal numbers for what we called A and B the other day, so this is A, this is B, then it dimples, right? It has that kind of cardio, it looks like a regular heart. So there you go, that's an exaggerated version of it. And if you remember, this was negative 2 and 2, whatever A was, were those intercepts. A plus B made the upper called major axis intercept, and then the minor one was the difference between the two, so it hits at the origin of 0. Those are all key features of that particular graph. The deal is I want to find the area bounded by that whole graph, which would mean the whole thing. So I do intend to find the whole area. So if I just shade, I want all of this heart. But the way I'm going to go about getting it, though, is I'm only going to do part of it. Just to give you an idea of kind of one of the strategies that we can often use with these is that we actually only do part of it. We're going to do sectors from one angle all the way up to another angle, and then we're just going to double it. So if we just do it to between those angles, sectors fanning out in that direction. The thing you want to know is you always want to find out there's some key places to start and stop your areas, and there's key thetas that you want to think about, and those are your polar origin, your vertex right there that's starting. It's really interesting to know where the pole, where your polar graph hits that origin, where it touches in there, called your polar zeros. And those end up having a pretty big implications for when you want to find the area. So polar zeros It's when the actual polar graph, your radius is 0. So a quick way to find it is 2 plus 2 sine of theta. And they kind of give you a baseline piece of information. And you set it equal to 0. And you do all your regular algebra stuff, subtract 2 and divide by 2. And if you notice, you get sine of theta equals 1. And there are many solutions. But we're thinking about one of the other parts we have to keep in mind too is that a cardioid has a certain domain that carves it out, makes a whole picture of it. And if you remember our little investigation, it took us from 0 to 2 pi to create an entire cardioid. So those are the values of theta we're interested in solving for in this little equation. So when I say, when does the sine of theta equal 1? I'm thinking of pi over 2. And that's the only one that satisfies. And that means facing straight up. So if we do that, so sine of theta equals 1. And actually, I meant to put negative 1 on there, didn't I? So back up, 3 pi over 2. When I put negative 1 there, it makes a difference, right? When you subtract 2 from both sides and subtract 2, you get the idea. But subtracting 2, 3 pi over 2, so you're facing 3 pi over 2, and that's when you have a radius of 0. And I'll put that in there just to give you kind of an image that goes with it. That means as I'm facing down 3 pi over 2, my radius is 0, and that's where I'm hitting that polar 0. Now that's one way to describe it. The other way to describe it that I might even use for this integral is that you are welcome to describe the angle 3 pi over 2 as negative pi over 2. Can kind of be helpful because when we do this integral here in a minute, we want to go from low to high. And if you refer to that as negative pi over 2, it just makes the writing of the integral somewhat easier. So here's how it goes. Here's your regular formula for area of a polar curve is to take the sector formula. So 1/2 r squared d theta, and our lower angle that creates that region that we swept, I'm going to call it negative pi over 2. And then where does it stop? It looks like the region that I'm interested in it would stop when I'm facing straight up and facing that direction. You never want to make that assumption. You always want to be extra careful. So sometimes it's nice to put in some numbers too, just to have a sense of when certain points are plotted. So if I put in 0 into my radius that I've been given, 2 plus 2 sine of theta, so I'll write it out here so I don't have to keep looking around. Okay, 2 plus 2 sine of theta. If I put in 0, the sine of 0 is 0, we get out 2. So the first point that gets plotted is actually out there on the edge, on that corner over there, okay, or on the x-axis, sorry. So put that back, use a different color so it stands out a little bit. Let's go with like we'll do bright blue again. So that was 2. We plotted it here on the edge. And then when we put in something like, pi over 6, we put that angle in there. So pi over 6. Sine of pi over 6 is 1/2. 2 times 1/2 is 1. 2 plus 1 is 3. So we actually, if we're facing pi over 6, we go out a radius of 3 and plot a point. Now, then we get to pi over 2. You just want to be confirmed. It looks like it's going to go straight up. It does, but you always want to be extra sure that it's not a negative radius, because sometimes when you put in a particular angle, your radius is negative, and you could be plotting a point in the exact opposite direction. So be careful of your assumptions. Sine of pi over 2 is 1, 2 times 1 is 2, 2 plus 2 is 4. Bingo. When I put in pi over 2, I do in fact get out 4. That confirms that the angles that sweep that region, the area of interest I'm looking at, are negative pi over 2 all the way up to pi over 2. And that will sweep the appropriate angles that I've denoted up there in those little blue sectors. Now remember, that's half my cardioid. Inside here we put 2 plus 2 sine of theta, the actual radius that I've been given. And there you go, that's the area of 1/2. And then of course we want the whole cardioid, so all you have to do is take that area and double it, and we have a winner. There's the area of that cardioid. There's other ways to take it on, but we love to take advantage of in polar as you can. You want to also take advantage of symmetry as I did there. So if you can do half of something and double it, it's going to be worth your time. Sometimes you can bypass that. It's not a mandatory thing, but there are times when it's advantageous. So on we go. We're going to scroll, scroll, scroll. One petal of one of these rose curves is our next one. And if you think a sine curve is one of those that it has a certain type of symmetry, we're going to see here in just a minute. 3 is an odd number, so we're going to actually have 3 petals. If it's an odd number multiplier to theta, then it's the number of petals matches the multiplier. And then 2 would be the length of the petals, because the maximum length, the radius would hit a maximum of 2. So those are things that we'll keep in mind. I'm actually going to plot some points just so I know where to start and give you practice on trying to think through, if I put in 0, where does this thing start? If I put 0 in for theta, sine of theta is 0, and we get 0 out. So it does start at 0, 0 when you put that in there. And then if you go to another nice angle, now think about what you're doing. You're tripling whatever angle you put in there. So sometimes your choices, I'm going to be careful. Like I'm going to choose pi over 6 this time. If I put pi over 6, 3 times pi over 6 is actually pi over 2. Sine of that is 1. 2 times 1 is 2. So when I'm facing pi over 6, I actually go out 2. You want to note that's your petal length. So what you just did is you have just, going to that angle, created your full length petal. It makes me think, ooh, my next, I'm going to be coming back. That's the tip of my petal. It doesn't go any further out. If you've reached a radius of 2, you know you're at the tip of a petal. Then I'm going to put in one other, let's do pi over 3, or pi over 4. Would that work? Yeah, pi over 4, the next one, kind of along the unit circle, as you know. 3 pi over 4, because I'm multiplying by 3, sine of that. Doesn't make a particularly nice angle. That's what sine of 3 pi over 4 is going around the bottom end. It's one of those square root of 2 ones, so negative square root of 2 over 2. Or is it positive? Yeah, positive square root of 2 over 2 times 2, so it's just square root of 2. And it's nothing fancy, it's out there. 1.41-ish, so you can kind of just find a decent spot to plot it. And then pi over 3. If you put that in for theta, the 3's cancel. Sine of pi is 0, and so we get out 0. So we're back to the origin. So we just carved out one petal there, going from 0 to pi over 3. There's two approaches you could have taken to this and how we could get that area of one petal. You could take advantage of symmetry. So half goes up front and gone from 0 to pi over 6, knowing you had half of a petal at that point. And so let me zoom in on that and cut it in half for you. That's half a petal when we got there, so we knew that we could do sectors up to that point and then just double it. And it chose green, looks like a leaf. And that would work. You could also just keep going and do the whole thing all the way up to pi over 3. By the time you get to pi over 3, you have worked your way around to completing the entire petal, and the areas of the sectors would complete from there. Get a different color, go blue or something like that, and that would give you the rest of these sectors all the way till pi over 3. Either one is just fine. I'm just going to finish out these. I'll just write them both. The radius is the same, 2 times sine of 3 theta. Either way you look at it, d theta. And then square it, of course. And then you have to take 0 to pi over 6 is only halfway. So in this particular instance, you want to double the whole thing to get the area in one petal. Now this is a 3-petal flower. If you wanted to get the area of all 3 petals, you of course would then take this result and then triple that. So the symmetry of these polar curves is helpful, knowing that all the petals are the same area in a rose curve. The hemispheres of any cardioid are the same. Lemniscates, both halves are the same. They're symmetrical in every way. Here's the other option. Remember, we can do the whole thing in one fell swoop. We could have gone from 0 to pi over 3, and you'd have yourself the exact same quantity. So multiple ways to get at the results. Take advantage of which one helps your situation best, but they are equivalent to one another. And we'll get to the algebra and doing these by hand. Right now we're just setting them up and then using the calculator to confirm that they're equivalent, and then we'll do the algebra next week that goes with this, because it's some pretty cool stuff how to do it by hand. We got another one, area of this particular petal. Do this